Hello, everyone. Welcome to the Antenna Theory for Wireless Microphones webinar with our special guest today, James Stoffo. Very happy that everyone can join us here today. Before we get started, I do have some brief introductions. First off, I'm Brian Grahn with the TC Furlong sales and marketing team. For those unfamiliar, TC Furlong is a Chicago area-based live sound company. We specialize in pro audio equipment sales and rentals, live event production, and specialty services, including loudspeaker system design and alignment, RF coordination, and repair services. We've been renting wireless microphone systems for over 30 years, have a wide array of microphones, IEM, IFB, intercom, assisted listening, wireless systems in our inventory. We're also dealers for all major professional audio brands. So our company slogan is better audio by design, and that means every sales or rental system that we spec is always custom designed and tailored for specific applications. All right, so before we jump into today's webinar, I do have some housekeeping. First off, we are recording the webinar today. We plan to post this to our YouTube page. We'll make sure to follow up with everyone with a link to the video once it's up and running, probably about a week. Also, please use the Q&A feature in Zoom to ask any questions during today's webinar. We do have a designated Q&A time at the end of the event, but please ask questions as we go. We can prioritize certain questions over the course of the event today as well. So today we are joined by James Stoffo. James is a leading RF technician and frequency coordinator on large-scale special events and installations. He's also a founder and chief technology officer of Radioactive Designs, a manufacturer of wireless intercom systems. James has worked as the frequency coordinator for many high-end special events, including the World Cup, multiple NBA All-Star games, NBA Finals, and Rose Bowl games, and as the frequency coordinator for the Society of Broadcast Engineers. Our company has had a long relationship with James, stretching back many years, and we're so happy that you can be here with us today, James.
Hey, thanks, Brian. Thanks very much. I appreciate you asking me back. In fact, when I was way back, just started professional wireless over 20 years ago out of Orlando, Florida, I ran into TC. It was around 2000, actually, when all the rumblings of digital television started. And he's the one who said, hey, have you ever spoken publicly or presented? I'm like, well, not really. You want to give it a shot? So really, it was TC Furlong that got me into the whole practice of, having these wireless discussions and webinars. But back then, we did it on literally an overhead projector, and I faxed him on a fax machine all of the material, and he put it together for the transparency. So it's different times. So I'm glad that, you guys I'm still welcome. And I appreciate you having an opportunity to connect with so many people. I recognize the names on the list of attendees, and look forward to the day when we could all see each other at a trade show or in person at a show. And for now, it's just nice to know that people are out there and we're able to see each other.
Definitely. And so happy you could be here with us today and everyone could join us here for the webinar. I do want to note that today's webinar is the first in 2 webinars with James. Today we'll be discussing antenna theory for wireless systems, but on June 22nd, we will be discussing large strategies for large-scale deployment, including band planning, coordination, zone planning, etc. So we hope to keep today's discussion mainly to antennas. So please join us on the 22nd to dig a little deeper into larger system coordination tactics. Aaron, I think, can drop a link to the sign up for that webinar in the chat as well. And when you sign up for that event, if you have any specific questions you have that you want us to answer, we're happy to look at that in the registration pages and help tailor the information that we'll cover during that next webinar. So with that said, James, I know we got a lot to cover today for antennas. I'll turn it over to you.
All right. Okay, thanks very much again for the invitation. And, an hour is not a ton of time, and that's why we decided to break this up into two separate webinars. And it's even if I talk fast, we'll not get through everything that needs to be discussed. But the bottom line is this, and anybody who's worked with me knows that the most important component of the wireless microphone or intercom or in-ear monitor system is the antenna itself. I could take a $100,000 digital Sennheiser 9000 and a $65 Radio Shack special, and I can cause the Radio Shack wireless microphone to work better than the $100,000 Sennheiser system for 8 channels, just by simply the proper use and misuse of the antenna. And anyone who's worked with me knows that I spend a lot of time thinking about where the antenna is going to go. It is the head end of all that's downstream of it. It is the one component that will convert all of the RF noise in your environment into either having good audio quality and good wireless range, or dropouts and bad audio quality if it's an analog, or more dropouts if it's digital. So this will specifically discuss for a while the different types of antennas. Very little theory. In fact, I changed the title to Theory and Use. And the reason for that is the better the signal to noise ratio in the RF world, the greater your range will be with an analog or digital system, and the greater your audio quality could be. We're also only going to be discussing low power auxiliary devices, wireless microphones, intercoms, and in-ears. This we're not going to be providing any information on the higher power devices, like maybe a specialized antenna in the back of your car that's pointed behind you to shut down the police cruiser that's chasing you. That's a discussion for backstage. But this one will be on low power. So let me get into my PowerPoint here. So again, Chief Technology Radioactive Designs, but I was the founder of Professional Wireless Systems, and which now they primarily manufacture accessory products. Chief Radioactive Designs wireless intercom, of course, and some accessories. So really, at its most basic level, all an antenna is a metal coat hanger that you stretch out into a straight line. And when you send an alternating current of any power level into the coat hanger, assuming it's straight enough, like a whip antenna, it will radiate electrons. It's going to convert it has to be a metallic object. If you were to take a 5,000 watt audio amplifier and put it into a speaker, it would take an electrical power, some electrical source, and it would convert it to sound pressure levels, because the transducer is the component that converts electricity into sound pressure. So we're converting energy, we're not creating it. If you take that same 5,000 watt amplifier and plug the speaker terminals into one end of a coat hanger and the other end into ground, that abundance of energy will create an electromagnetic field as opposed to an acoustic field or sound pressure level changes. Now, the reason that the radiation pattern of the antenna looks the way it does for this is just a regular old common whip antenna, is because the greatest aperture, the greatest amount of surface area of that antenna is on the side of the antenna. If you were to turn an antenna straight up and down and look at it from the top, you wouldn't see very much of it. Whereas if you turn it sideways and then you're looking at it from the side, you'll see much more of it. That's your visual energy. Well, in this case, it works the same way for radio frequency energy. So you'll have the greatest amount. So if all you have is a whip antenna, the way you're going to get the best range out of it is by pointing it perpendicular to your source, if that's all you have to work with. RF does travel at the speed of light through space. There are two components to it, the electric component and the magnetic component. Those two components are 90 degrees out of polarization with each other. And when people say, hey, I want you to vertically polarize this antenna, in other words, put that paddle on a mic stand, we're referring to the electrical polarization of the antenna. Here's just another look at the radiation pattern. This is just a straight whip antenna. It's called the Doughnut reception pattern, probably because it was named by a Gentile, because it looks more like a bagel to me, but it is called the Doughnut pattern. And again, it's radiating at its greatest power levels off the perpendicular side, because that's the part of the antenna that you see the most of. In fact, here, grab a little. This is just a regular standard whip. you could see a whole lot of that whip off the perpendicular side. As I start to turn it towards the camera, now you only see this small amount of it. If somebody said, hey, go out in the woods and go find this antenna, if you saw this side of it, it would be very difficult to see. But if you saw this angle, you'd see, obviously, that's a straight antenna. And again, this is using the visual energy and frequencies that the human body has the ability to see. RF acts the exact same way. The RF will see the antenna from its greatest surface area. Okay? Just another basic principle. And again, that's called the Doughnut reception pattern. Any array of antennas is simply an array of omnidirectional antennas that is positioned and phased in such a way as to create directivity, and we'll talk about that in a minute. The three big components to know about when you're dealing with antennas are polarization, reciprocity, and resonance. Polarization is what I just talked about, where we have an antenna either vertically or horizontally polarized, and what that means is if the antenna is called vertically polarized, that means it's perpendicular to the earth, okay? The earth is ground for an antenna. A vertical polarization means that it's perpendicular to the earth, to ground. Horizontal means that it's horizontal, it's parallel to the ground. That's all that is, polarization. But it comes into play, especially when you start to talk about wireless microphones, low power devices, and point-to-point links. If anybody uses like a Shure in-ear transmitter or PSM 1000 with a bunch of wireless mic receivers like UHFRs, you could put into the same sort of tone code squelch so that they speak the same language. Well, polarization becomes very important when you want the transmitter, which is stationary, and another receiver, which is stationary, to have maximum transfer of energy. Reciprocity is the good news. Reciprocity essentially means that all of the characteristics of an antenna, the radio frequency coverage area, the bandwidth, the actual bandwidth of the antenna, the beam width, which is the polar pattern, let's say, whether you're talking about a transmit antenna or a receiver antenna, they are equivalent. All of those characteristics will be equivalent, whether you use that antenna for transmit or receive. So the good news is you only have to learn it once, and it applies to whether you're talking about a wireless mic receiver or an in-ear monitor transmitter or a comm transmit or receive. That same antenna will work in an equivalent manner, whether it's used as a transmitter or a receiver. Resonance is also another important aspect, the property of the antenna. And all resonance is, it's just like anything. And I make a lot of references to the ocean because I love the ocean. I live on the ocean. I observe waves in the ocean, and they all propagate and behave very similar to RF waves. Resonance simply means that there is a relationship, a harmonic relationship between the size of an antenna, the length of an antenna, and the radio frequency that you're operating with. So in other words, if you're on a show and all of a sudden somebody comes up and says, oh, you know, I lost my in-ear receiver, I'm taking in-ear dropouts is the way they'll say your in-ear's not working. And then you grab the pack and the antenna's not on it. Well, technically, when you grab a new antenna, you want to grab one that's at least close to the same frequency of that pack. And if you don't, you will not have harmonic resonance and you'll have less than a perfect signal. So what we're trying to do is maximize our chances for success. You could play every rule in the book, as I tried to do, and still something is always going to happen, usually right before showtime, before downbeat. So, but if you take advantage of every single trick in the book, you will maximize your chances for success. And that's the best we could hope to achieve. I was called in by a bunch of producers. I won't tell you which company it was. And they said, can you guarantee us 100% that we're going to have success? I said, no, I can guarantee you 99.998%. And that's about all I could do. Here's a really important thing. If there's nothing else you walk away with today, or hang up the phone, or however you're dialed in here, remember that the Zen of wireless, you must always look at the world from the receiver's perspective, because now it really should be the receiver antenna's perspective. And I'm going to change that. It should be receiver antenna, because my wireless mic receivers might be not only backstage, but back in the tunnel of a stadium. And when the microphones walk out on the stage, maybe it's a field or a concert venue, if I had antennas way back by my receivers, they wouldn't even see the RF, right? But when I look at what those receivers are going to see, I have to focus on where that receiver antenna is, whatever kind of antenna it is. If it's an in-ear monitor system, where is that antenna? It's on the artist's pack. So now you have to think about, when you're placing your in-ear transmitter, where is the receiver antenna going to be? If it's on an artist's pack, and the artist is, walking around the mosh pit surrounded by LED walls, well, that's going to cause you to change where you would have placed your in-ear monitor transmit antenna to accommodate that particular scenario. So there's another second thing. I'll probably say, if there's only one thing you take away, it should be this. Well, here's another one of those things. Always look at your world. If you're a comm system, where's the paycheck? Who's writing your check? Who's your boss? Who's the tech manager? Where do they expect that comm to work? Does it have to just work on stage? Does it have to work in green rooms? Does the audio department need to go out to a music truck and set up staging? Does the producer smoke? So you want it to work out by the ashtray. So, you need to find out what is the expectation, and then look at the world from that receiver antenna's perspective to accommodate that request. So what you're looking at here, this is courtesy, by the way, of Joe Chowdelli at Sennheiser, good friend of mine. Hello, Joe, if you're listening. What you're looking at is an actual level of voltage at the receiver antenna as a person wearing a body pack transmitter walks across stage. Now, in this case, you could see that's really good antenna placement, because the average line that you could see with those few dips in it is pretty good. 1,000, the dynamic range of a wireless mic is really quite incredible. You could have your squelch threshold set as low as 1 or 2 microvolts and go all the way up to 1,000 microvolts. And that's what the front end of a wireless microphone could take. That's a lot of dynamic range. In this case, the average signal is over 100 microvolts, which is more than enough. I generally squelch my analog systems down to about 2 microvolts, or right above the RF noise floor, whatever it may be for the room. In this case, if I were setting the squelch, those dips may not cause a dropout. If you were one to set your squelch a little higher for some reason, or your noise floor was high and you had to set your squelch higher, then you'd have a couple of dropouts, probably those bottom 2 or 3 dips that go below 10 microvolts. So what you're looking at here, in my opinion, would have happened because of a polarization dropout. Polarization dropouts are when the RF hits a wall or a metallic surface and flips in polarization. So if you had a handheld mic, or here's another scenario, someone has a handheld mic and it's a dipole, and they pick up the mic to sing sideways, and suddenly now that RF is traveling through space on a horizontal plane, and your antenna is on a vertical polarization. Those dropouts look to me like they would be either polarization dropouts, maybe multipath cancellations. Getting ahead of myself, that's June 22nd. We'll talk about that a little bit. Here's a couple of really common antennas that we could find anywhere. The dipole, that's Electrosonics dipole. The ground plane, I think Audio-Technica was the first one to start shipping it. And then Garwood, which was the first in-ear monitor company in the world. They introduced wireless in-ears many moons ago. These are all omnidirectional antennas. The bottom antenna is a disc cone. The only reason I put that there is because I showed up one time onto a show and the antenna kit didn't make it. And you can buy that disc cone antenna at Radio Shack for $50. And it covers everything from Comtech VHF down in 72 meg all the way up to 900 meg. It's a very wideband omnidirectional antenna. It's got a little bit of a funky reception pattern there. As you can see, it's sort of like, I would describe that as almost a funnel, whereas the ground plane's obviously truly a funnel. The disc cone is an upside down funnel. And then the dipole will have just a standard omnidirectional donut reception pattern. By the way, I almost never use Omni antennas. These are very basic antennas. I use them when I do an RF sweep because I want to find out what's coming in from anywhere. Once I get into a show or rehearsal mode, it's all directional antennas. The only place I might put an Omni is in the scenario I mentioned earlier, where the stage is out on a field or in a performing arts venue, and the wireless receivers are backstage. So I have my, you might have your wireless microphones backstage, and you have to test them before you hand them off to go out on the stage. Well, to listen backstage, I usually just get a BNC-T connector or a proper two-way passive splitter and just pop a little whip antenna back behind the rack so that I can pick up the transmitters backstage. If I didn't have the antenna backstage, I wouldn't be able to test before I hand it off to know that it's going to work when it gets to my real antenna system to cover the show. Other than that, I use pretty much one of the following antennas here. This one is the most familiar to everybody. This is also from Electrosonics, by the way. My buddy Carl Winkler at Electrosonics, a great guy. Almost every wireless manufacturer makes a version of a paddle antenna. You've heard it called a shark fin, although you won't hear me calling it a shark fin because I've seen too many real shark fins when I'm scuba diving, and I get a different reaction than I do from them from when I see this shark fin. This shark fin doesn't scare me. It gets my attention, but it doesn't scare me. So I call them, you can call them a paddle, but it's a log periodic dipole array, because if you look, even though it's an array of dipoles, as you can see on the bottom of your screen, the bottom right here, if you look, when you see these antennas, they just look like a flat paddle, like a ping pong paddle. But if you look a little more closely, you'll see that there are vertical lines, and that horizontal line is the feed point for all of the dipoles that are in tandem there, and they're lined up in a logarithmic fashion to create forward gain. Dipole's a nice basic antenna. It's always great to stick one in your backpack or in a rack drawer. Certainly nothing wrong with the dipole, other than it's kind of like a grandfather clock that hasn't been wound, or an analog wristwatch that's broken. It's still right twice a day, okay? But as soon as you go off axis with your RF transmit signal, you will get a dropout. This is a singularly polarized. In this case, it's a vertically polarized, and if you put it on a mic stand, it will be vertically polarized. Therefore, if the RF is traveling through space in a horizontal polarization, you will get a dropout, or at least you'll see all of the RF lights on the receiver dip and cause your stomach to growl a little bit. So in any case, just remember, this is a great antenna. It's got forward gain, but it's only got one single polarization. 6 dB is more than enough gain. It's the multi-polarization that we're interested in to maximize our chances for success. So that top one there, these are all directional antennas. By the way, it is passive gain, which means that you'll get anywhere from 6 dB to as high as 12 dB over a dipole of gain. So that's a lot of forward gain with no RF noise from an amplifier. I always carry a couple of those Shure Inline amps that they are powered up the coax by 12 volts DC, and they have a 3 dB and a 6 dB switch. PWS makes them as well with a 5 dB and a 15 dB. There's a couple of manufacturers that make their own version of that. But I love carrying those, but they add RF noise. And whenever you have an active RF device in any radio circuit, you can introduce intermodulation distortion, which we'll get into on the 22nd really deep. But the bottom line is a nonlinear device is required for RF signals to mix and match. Okay. And by nonlinear, you could have a rusty antenna creating an NP or PN junction. That's enough nonlinearity to create intermodulation distortion, or the active mixing of multiple RF signals. These antennas are all passive. So you get, like in the case of the helical, which is the granddaddy of them all, you get 12 dB of gain over a dipole, and that's passive. Well, that's as much gain as an RF amplifier that's adding at least 12 dB of amplifier noise from the electronics in the circuit, right? So I'm always going after passive gain. I have a pocket full of various RF amps, but I don't use them unless I absolutely have to, and not until I have someone walk all of the transmitters out onto the stage and into the audience and the furthest point that anyone expects that mic to work, and only as much as I need. Like when I use the Shure Inline amps, usually keep those to 3 dB. When I use the PWS, I keep them to 5 dB. I always start with the least. You always want to start, you know, more is not better, not necessarily. In fact, if you, let's say, for example, a typical show, let's say you had 6 or 8 in-ear monitors, okay, and a rad combiner, which you can kick up to 1/4 watt on each signal. Well, that's 2 watts of radiated power now. You put that next to your wireless microphone receivers that are looking for these minuscule, minute microvolts of RF energy, and that 2 watts radiated is going to splatter onto your mics and create interference. And all you have to do to get your mics to work is turn your in-ear switches down to 50 milliwatts, and that covers the stage just fine. So in other words, more is not better. What really is needed is just enough to get it right. And really, I wish there were a magic answer on what that number is, but unfortunately, as long as set designers continue to create different sets, and as long as we start to operate into different venues, there will always be a unique situation. So that's why I'm trying to stick with the basic fundamental information here, and then you have to use your mind to picture what's going right and what's going wrong. You know, I generally don't start with the most power. I start with somewhere in the middle, you know, or the least, and work my way up. Now, you can see that circularly polarized antenna, that happens to be the inside of a Sennheiser, I think it's CP5000. You can see it's a very long metal coat hanger that's wrapped in a big circle. That's what it is, essentially. So, in fact, if you really get stuck in a jam on a show, you can go to costuming and grab a metal coat hanger and use that. It'll work. It won't be great, but it'll work. That's all these antennas are. The helical as well. It's you know, a bunch of screen door parts, but they're just put together in the right way. The thing I really like about multi-polarized antennas is that unlike the log periodic, where if we come at it if the RF happens to spin off of axis and travel through space on a horizontal polarization, you'll get a dropout. But with a circularly polarized antenna or a helical antenna, it doesn't matter which way the RF is spinning through space. You will always have 100% energy transfer between that RF signal and the receiver antenna. And for you in-ear monitor folks out there, guess what? If you put and those of you who have worked with me know, I always try to get you to use, and nobody usually says no, but I always try to you know, implement the use of that second middle antenna, which is a CP, circularly polarized, not a helical. The reason for that is that the CP antenna has a much wider polar pattern, and you only have one transmitter, whereas the helical has a much tighter pattern like a spotlight, but because of diversity receivers, you can place a couple around to make up for where your dropout zones. So what I was getting to was, when you transmit out of a CP antenna, the RF signal is going like this, through space. It's traveling all through every polarization through space, and it's doing it probably 600 million times every 2 feet. So the chances of it, but by the way, even if you took a dropout, if there was a complete out of polarity signal with your in-ear monitor receiver antenna, which is just a whip after all, it's just a whip antenna on a body, like it can't get any worse conditions than this. Let's get a sweaty body dancing with conduction against the sweat and the body, and throw the worst possible antenna on this device you could have, right? That's what an in-ear receiver is. So you need to do as much as you can on the transmit side to get that 100% transfer. So I always recommend a CP or helical antenna for transmitters.
James, I've got a question from Lucas here, and this is actually a great question of, you just mentioned in-ear monitor antennas are typically just going to be a Omni dipole. But how come we never see a circular polarized receive antenna on an IEM pack? Is it wavelength size? Is it just the physical size of the antenna needed along with that?
I wanted to do this on Broadway in the 1900s. I wanted to use a patch antenna, a fractal patch antenna. I can't believe nobody's doing this yet. I think maybe Shure's MicroPack might now implement some type of patch, but someone from Shure is going to have to verify that. But I've been wanting to do this for over 30 years. Get rid of the whip, go ahead and use the SMA connector. And what I was told by many manufacturers at the time was it's a licensing issue. You have to license this antenna. I think that might not be the case anymore, but absolutely there is no reason why we should not be using fractal antennas, patch antennas, anything but the whip, and stick it on the outside of the pack, which is away from the person's body and probably the driest spot from all the sweat. And it's aiming outward away from their body. There'll be the least amount of absorption, if any. So yeah, that's a great question. And the answer actually gets me really mad because I wanted to do this 30 years ago. And I think maybe by now, Shure might be the only, and if somebody in Shure is listening, they can chat in and verify that or not. But yes, absolutely, there's no reason. So if you have access to a fractal or you want to cut out a screen door and make your own and solder it to an SMA connector, absolutely, by all means, great idea. Sure. Absolutely great idea.
And can you talk, this is actually a question from, I believe it's Odysseus. What about fractal antennas, the pros and cons compared to helicals and circular polarized antennas? So can you talk about fractals just a little bit?
Sure. So fractal antenna doesn't have a ton of gain. So I have played around with fractals. We're talking now not on a human body. Obviously, we're talking about a backstage up on a panel somewhere. I think Claire started using them a bunch of years ago, and I did a lot of testing. And the bottom line is there's no comparison to a helical or a CP antenna. There's just no comparison. You don't have the gain, you don't have the directivity, you don't have the extent of multi-polarization coverage that you get, and they're also not readily available and they're not cheap. So, that's a bunch of reasons why not to use it. If Shure or Sennheiser or someone comes out with a fractal antenna that's usable and could fit in a rack drawer, I mean, that is something nice about it. It fits in a rack drawer, which is kind of nice. But these other antennas are readily available. They're not priced badly for what you get out of them. And in my experience, the fractal was what I consider to be not as good. It was an inferior antenna to these other antennas we're talking about. Now, it's better than a whip. So on the body pack transmitter or an in-ear receiver, yes, it's 10 times better. Yeah. But when you have these other antennas to choose from that you can mount wherever you want on a drum kickstand under a stage, there's no comparison to that. Sure.
And our next question from Sam here, I think might lead us into the next slide or our next conversation is, in what situations are we choosing CP over helical or vice versa? And, how are you using, maybe kind of expanding that question, how are you using the directivity? Like, when is that applicable of CP versus helical?
Best way to look at these antennas, since you can't not see RF, there's no one that I know could see RF. There are some creatures that could perceive it, bees and stuff. And if you can see RF, please email me, you're hired. No matter what you do, if you could see it, you're hired. But we can see light, and you can imagine light. So when you look at these antennas, picture a spotlight, okay? The helical is a very tight spotlight, but it's really bright. The CP is a softer spotlight with a wider gain, and it's not as bright. In other words, the RF, there's not as much energy. You won't have the forward gain that you get out of a helical, but you'll have a wider coverage pattern. Incidentally, I should mention, and the guys and gals who work shows with me see me do this, if you have a very wide stage and there's a lot of lighting or some scenic that will block RF from backstage, you could absolutely put an array of those CP antennas, the middle ones, or helicals, under the stage on a drums kickstand pointing up. I usually put them upstage, below the stage, so they're under the scenic metallic or lighting walls that are going to create your problem. And I point them out so that they're covering the stage and the artist can still go out into the audience and have coverage. In fact, usually the coverage is better at the back of the house than it is on stage because of the interference from the light walls. What I was getting to is, though, you can actually use a high power two-way combiner, which PWS manufactures those, very inexpensive. And you could daisy chain multiple CP antennas under the stage to cover a wider stage. The thing you have to remember is every time you split RF, you lose 3 dB. Mm-hmm. So if you have two antennas off even a BNC connector, and your Shure is set to 100 milliwatts, you'll only get 50 milliwatts to each antenna. But if it's an FM system, which all the in-ears are on the market that are used as in-ears, the only one that's not, to my knowledge, is Electrosonic's digital duet system. But for FM, there's a function called the receiver capture effect. The FM in-ear receiver will only lock onto one of those antennas at a time. And just like a cell tower, when you go from one to the next and you roam to a different node, the receiver will not switch and feed audio to the in-ear buds until the signal from that secondary antenna is 6 dB hotter than the one that's locked onto. It's just a function of FM. And I tested this out multiple times with a spectrum analyzer in my hand, walking from antenna to antenna. And by the way, that switch occurs so fast that A, the electronics in the in-ear receiver can't pick it up, and B, even if it could, our human ears couldn't pick it up psychoacoustically. So that's another trick if you have a really wide stage. More to the point of the question, helical versus CP. I wouldn't use a helical on in-ears if I were close to the artist, because it's too tight of a pattern. And I've had in-ear monitor guys tell me that when the artist walks just out of that very tight pattern, they drop out. And in-ears, I mean, think about it. This is the most critical of any audio device in the wireless world. There's an artist listening to it. They have no audio. There's no program going in. And all they hear is the noise of that receiver. It's the most critical you can get. You know, the only thing I can compare to is, you know, the national anthem at the Super Bowl being sung a cappella, where you're trying to cover, you know, 400 feet of range, and there's nothing to cover up any little glitch of that wireless microphone. So I really do feel for the monitor guys, especially the ones that have to put the ears in the artist, and worse yet, take them out and hear the complaints. I get it. I totally get it. I have guys that I work with, gals that I work with, that they're like, hey, James, I'm taking hits. And, you know, you do what you can. Sometimes it's a frequency issue. Sometimes it's an antenna placement issue. But hopefully there's enough time to resolve it before showtime.
Sure.
And a lot of these don't unmask themselves until rehearsal, when it all hits, you know, the fan and all of the elements are up with video and lighting walls and all that stuff. So
sure. We've got another question from Matt, but I might save it for just a little later so we can keep going on with the presentation here. I think might be a question, and it involves some multipath discussion. So I'm not sure if that's coming up here soon.
We could talk about multipath. Sure. What's the question?
Well, I think the question is, can you passively split to both CP and helical antennas simultaneously? So I'm imagining this was for IEM transmit. And I guess in my mind, you know, when you start doing IEM transmit for multiple antennas, that's where you might run into a multipath issue. Okay,
so multipath would refer to a wireless mic receiver antenna and the RF signal from one microphone bouncing off the wall, flipping in phase 180 degrees, and then meeting itself and canceling out. Okay. Almost nothing to do with splitting and combining antennas, but the answer to the question, very good question, you could split to whatever types of antennas you want. You could have a coat hanger backstage, a helical stage left, and a CP stage right, and a dipole out at the truck. It doesn't matter. Just know that those antennas will affect each other. If you split two Omni antennas, you're going to create a phase cancellation that wouldn't be there if you didn't split at all. Whenever I split antennas, A, I only do it with directional antennas, and B, I point them in opposite directions, so that the chances of one zone ever creating a multipath cancellation in the other antenna is zero. The cancellation will happen in the cable someplace in between. Because in the case of the helical, the front to back ratio is 30 dB. So you would have to have a 5-watt signal on one side of the antenna to step on a 200 milliwatt signal on the other side. So that's why I use directional antennas when I split, and I never point them in the exact same directions.
Great.
Okay. This is just another couple of antennas. And if you ever work in Vegas and you're staying in your hotel room at the Mirage or the MGM, don't walk through the casino to work with that antenna on the left and stand behind the poker table. People get really upset. They might even call security on you. It's happened. So this is another one from Carl Winkler. I'm not going to spend a ton of time other than to say that what this relates to is signal to noise ratio through space. If you're in a very RF noisy environment, like those of us who are unfortunate enough to work outdoors in Miami at the stadium down here, Dolphin or Joe Robbie or whatever it's called this month, there's an antenna farm for all of South Florida that you can actually see from the stadium. It's about 1.5 miles. So there's so much RF there that if you walk out on a field with an unplugged fluorescent light, it'll start glowing, you know? So in that case, you would want to put your antennas as close to the artist as possible and increase your signal to noise ratio. The noise is the RF from the television. The signal is your wireless mic. In that case, running a long cable is completely acceptable. If you're in a very quiet environment in a studio where there's no RF interference, then you don't need the RF cable because it creates loss. Look at all the loss in this case. 250 feet, I would never run, but 10 dB of loss at certain frequencies. So in other words, and we're going to get into this here in a minute, but that's what Carl was trying to say here is coax versus over the air. And the big question is there RF noise in the air or is there not RF noise in the air? That's really the fundamental question when it comes to this. Because here's the loss through RF cable. This is typical coax cable. As you can see, as we go lower in frequency to VHF, where the radioactive design stuff is, we have very low losses. But as you go up higher in frequency, where the top end of the legal limit is, we'll get into that more next month, but we have over 3 times the loss at those frequencies. So I generally try not to run more than 100 feet of cable. If I do, I'm definitely using a gain antenna. And if it's more than 100, well, I try not to run more than 150 feet. If you do, now you're implementing RF amplifiers and things of that nature. By the way, anyone is welcome to this PowerPoint. If anybody wants it, they can reach out to you, Brian, or to me, or Aaron.
That's great. We appreciate it.
So we want to look at our operational area. If you have the ability to do a sweep with a radio spectrum analyzer, great. If not, turn on your wireless receivers. If you see RF LED lights, that's interference. If you see LED lights lighting before you turn on your transmitter, that's not good. So you could even use your RF, and in fact, Shure and a lot of other manufacturers now, and I know RF Venue even has a specific component where they have a spectrograph built into a rack display. So you don't even have to buy a $25,000 Roden Schwartz anymore. You can get a fairly reasonably priced one. But look at your area. The people who have worked with me on shows know that once we get into show and lighting continues to add light panels, the noise floor goes up on stage. They'll come back and say, hey, James, I just started taking hits on this frequency and that frequency. And so you have to go back out and, maybe change a few frequencies or move your antennas a little bit. But you have to look at your operating area. Lights, incidentally, this is from Tim Veer at Shure, by the way. It's a very near field energy. So when you're dealing with wireless microphones and there's a big lighting wall, keep your wireless microphone antennas at least 20 feet away from those light walls. Keep your receiver antennas 20 feet away or more and up as high as possible if you're indoors. Outdoors, it's a bit of a different story. But the point is, the light walls are very near interference. Don't freak out if you had your shark fin clamped onto a lighting wall and you're getting interference. Unclamp the paddle and put it on a mic stand 20 feet away and that problem will go away. I wasn't going to say every problem. You could use a paddle or a directional antenna like a helical to direction find. If you find a TV, antenna farm, there's nothing you can do about that. But if you find 2 IFB transmitters that are too close together in the ESPN booth, separate them by a foot or 2 and the intermod goes away. You could only find that with the use of directional antennas. You select appropriate antennas. Clearly, I like helicals. This was a Latin Grammys for Univision. Thank goodness for Univision. And, this was backstage. There was a light wall about 30 feet in front of me. And so we just kept everything back in the bleachers and it was nice and clean. We shot right through the light wall. Those are wireless mics and comms, and the antennas were under the stage and were probably more than likely for this one, CPs. Here's a guy trying to use a helical to bounce a signal, get some moon bounce. It's probably for an amateur ham radio operator. But the idea is you know, there is direction to these, and you have to be very accurate and point them to where the device needs to be. Now, here's a situation where we were at the Miami Super Bowl. I forget what year it was. Maybe I'm going to say 05, 06, something like that. And so there was a lot of RF noise. And I was behind those people. There was two women there that are wearing blue shirts. This is the national anthem with Carrie Underwood. And my antenna farm was behind those very big football players. And so Carrie walks out there on stage, and we had no RF at all. We had all Shure UHF Rs, and Tom Pisa was the monitor mixer. And he's like, James, is this the year we're going to have a hit on the anthem? And I said, no, Tom, it's not. And I handed my daughter there, that's Elise. She's holding a helical antenna down here, center screen to the left of that drummer. And I said, just go out into the field until the cameraman tells you you're in his shot, and keep going till you run out of cable. And so she was kind of in the middle of the field, green on both sides of her. That's a helical antenna. And one side of the Shure was pegged, and that's how we got through that anthem. But that's because we had low signal and lots of noise, okay? If that's your situation, that's when it's okay to use 100-foot of cable and get the antenna closer to the artist. This is a good reason to do that. Here's a different scenario entirely, where we're at risk of airwaves because we have a stage and the front of house is under that red and white tarp, and that's where the wireless receivers are. Well, now we have a lot of range between the stage and the wireless antennas. We also have a bunch of people. Now, there's one thing that RF does not travel well through, and that is organic material. Human beings are these big meat sacks, right? We're mostly made of water, and we absorb RF. In this situation, you want to get your antennas above the crowd's heads, but not much above the crowd's heads. In other words, the average person might be on the tall side around 6 foot. I wouldn't put the antennas more than about 7 foot high. The reason that I don't go for higher than that is because the higher you have an antenna, the more interference you pick up. This is why radio towers and TV antenna farms are way up on top of mountains or tall buildings. We don't have any of those in Florida, so we have to build big structures. But the reason that the transmitter is so far up is because they get more coverage. They have more market coverage. So the higher your antenna, the greater the range. Well, in this case, with a wireless mic, you don't want any range further than your stage. You want to pick up your stage and nothing else, right? So you get up above the heads of the crowd, get away from those meat sacks blocking everything, and then a foot or so, but not much more than that. Okay, there might be a couple of 7. If it's an NBA event, put it up 8 feet. You know, that's about all I could say. But you want to get above the crowd and not much higher than that. Here's a great shot. This was Stephen Copeland. We're really lucky to have Stephen working at Radioactive Designs. He's our customer service engineer, and he was on this Super Bowl with us. And so down there, you see everything. We obviously couldn't run CP antennas for the ears, you know, for the stage that's going to get wheeled out during a commercial break for the halftime show. This is all for the anthem and the halftime show. And so we couldn't run long cables and put them on the stage. We had to do everything from the side of the field. So this is a completely different scenario. Again, I'm trying to give you the tools and the fundamentals, and then you have to take these and process them into your own jobs, your own scenario. So we had, luckily this year, probably the last year that we had this much real estate on the side of the field. And Stephen was doing the comms, put the comm antennas, transmits to your left side of your screen. And then the wireless microphones more to the right, and then in-ears way over to the right. So we kept the mics away from the in-ear transmits. Very important to keep some distance between transmitter antennas and receiver antennas. I'm going to fly through some of this because we're getting tight on time. Diversity reception, for the most part, all that means is you have more than one antenna picking up the signal, because an RF dropout will almost never happen within a foot of itself. An RF dropout is a ball about the size of a tennis ball that travels around through space, and it's a black hole for your wireless mic frequency. It'll never land on 2 antennas at the same time, so you have a second antenna at the input of a wireless mic receiver to take advantage of when you might have a dropout on the first. So here's a scenario where we only have 2 antennas and we're splitting to feed, you know, probably 60 wireless mic receivers. There's a whole bunch of different ways to do that. This again is from Tim Veer at Shure. I always choose to go with the primary splitter there. Some people call it a master splitter. That's filtered loosely. In other words, UHF from maybe above my ears, which I do radio spectrum band plan. We'll talk more about that next month. But essentially, your bottom end of your wireless mics, say, is 500 meg. Your top end is 610 meg. Might put a filter there for that. And then at the outputs of those, I'll feed another bank of combiners, but they will have a much more precise or a much more narrow band filter, again, to minimize the RF noise floor. Because every time you split and add active amplification, you add noise. So you want to keep that noise to the most narrow band possible. There's a bunch of people that make splitters out there, professional wireless. It was one of I founded the company in '92. It's Mask Sound owns it now. They still do a ton of really great products, high end. RF Venue is another company that makes some really great splitters, a little more economically priced with maybe different bells and whistles. Radioactive Designs, we make wireless intercoms, but we also have the bottom there is a transmit combiner. We see them used not only for comms, but for in-ear monitors. Some different high power combiners out there. The one on top here is a rad unit that takes a couple of signals and splits it to 4 different zones with independent RF controls. You could put anywhere from fiber to quarter watt into each zone. So there's lots of tools out there. I talk a lot about filters. There's an RF Venue filter. There's Electrosonics filter on the left. Bandpass filters absolutely can save you. You can overlap several to create an even tighter bandpass filter, which is the bottom right graph there. You can use high pass filters for $38 from mini circuits and a low pass filter from mini circuits for $38. And for $72, you have an awesome little 50 to 100 megahertz bandpass filter. And what that does, it minimizes the noise going into your wireless receivers. There's some cavity filters, which are very tight. And there's your Shure amp on the bottom. An RF amplifier should only go in one place, and that is between the antenna. A filter should only go in one place, and that is between the antenna and the first active device. So the filter there is going to go, it's going to get the antenna fed to it, and it will feed the amplifier. So that amplifier from Shure goes from 470 meg to 950 meg. But you only care about 500 to 600 meg. So you're going to put a 500 to 600 meg filter in there so that Shure amp is not amplifying DC to daylight and picking up stuff that you really don't care about. Good. I made it with 5 minutes to spare. Great. 5 minutes to spare.
Yeah. Going back to the active inline amplifier. So, you know, in cases where an antenna does have an amplifier built into it. So for instance, you know, active antennas, as they're commonly referred to, what is your opinion on using that amplifier by default, or should you start off just with the passive gain that you would get out of, for instance, a directional paddle antenna, and then see if you would need to add any kind of amplification from there?
So my advice on antennas that have an amplifier attached to them is don't use them unless you absolutely have to. Shure just recently came out with one that does have an active switch. I believe it's +12, +6, 0, and -6 attenuation. If you're going to go with any antenna that has an active amp attached, at least buy one that has a filter as well. Because I've walked into places, people are having these horrible problems, and they have all their antennas on 10 dB, and they're not filtered well. And all I do is pull out the active antenna and put in the exact same paddle, log periodic paddle, without the amp, and it cleans up all the problems. As soon as you introduce an RF amplifier, you introduce noise, intermod distortion, you decrease your range, you reduce your audio quality in analog, and you create more dropouts in digital systems like a 6000 Sennheiser or a Shure AD. So, I mean, my advice is not, I know I'm probably not making some manufacturers happy because I already built them, but the bottom line is, I mean, I'm not a big fan of antennas that you cannot separate the amplifier with a filter. because now you have an unfiltered amplifier out there. Again, the only one I'm aware of that has a switch is a Shure, and hopefully someone can could answer this for me, because I don't even know if that attenuator switch is before the amp, after the amp. Does it bypass the amp? Regardless, if you're still using the full power of the amp, you're creating noise, regardless of whether you have 0 dB gain, 6 attenuation, 6 dB, or 6 or 12 dB gain. There's an amp in there, unless it's bypassed by that switch. If Shure says it's bypassed by the switch, you know, if Tim Veer or any of the people from Shure say, no, actually, if you put it to 0 attenuator, it bypasses the amp, well, then that's great. That's wonderful. I'd like to know that. So that's my answer. I'm not a huge fan, but in the case of the only one I know about, and I'm sorry if Sennheiser and Electrosonics or anybody else has an antenna like that I'm not aware of.
Sure. What are your thoughts about RF antennas over fiber?
Right. So there's a very specific need for that. And that is if your operating area is more than several hundred feet away, then it doesn't make sense to run coax. For one thing, it's very heavy. For two, RF over fiber is really coming into its own now. You know, just over the last couple of years, a couple of companies have come out with killer, top shelf. Zinwave is one. I think they're made in California. We use that at SpaceX for the radcoms that were put in for launches and landings and stuff. And it's all RF over fiber. PWS has one for show sites that's good up to, I think, 1 kilometer. If you're not going over, I don't know, let's say 250 feet, I would stick to coax.
Sure.
But RF over fiber comes into play. And there's also some pitfalls. RF over fiber is great for wireless mic receives. But when it comes to in-ear monitor transmitters or wireless intercom, you can't put any power into it. You can't put more than one signal. So ask any of the people that do in-ear monitors on this webinar how often they only have to use one in-ear. The answer is probably, I wish, not anymore. You know, there's usually 16 in-ears, and you can't do that with RF over fiber. So there are pitfalls to it. So if you're going to use it, I mean, use it when it's appropriate and know its limitations.
Sure. Going to go through, hopefully we can do some rapid fire. We've got a lot of questions. Hopefully we can get through all of them here. One from John Erskine here is right hand versus left hand circular polarization. Where do you use?
That's really awesome question. I love it. So here's the difference. If you use a left hand polarized helical is what they are, not CPs. The RF will travel through the space like your left hand, right? If you're right-hand polarized, the RF travels through space right-handed. Now, the most important thing to remember about opposite polarization with helicals is never use them for a point-to-point system. Because if you're transmitting with a left-hand polarized signal, a right-hand antenna will not see that signal. It'd be like really wrong. The way to remember that, Tim Veer gave me the best analogy. Put two bolts together and put a nut in the middle. And if you could unscrew the nut off of one right onto the other, then that's correct, okay? If you had, I don't know, some maybe from wherever screws are reverse threaded, in the middle, the nut's gonna stop, okay? Where you can use opposite handed left and right-handed helicals is maybe in an open field, you would use the left-hand polarized signal for your in-ear transmits and the right-hand polarized signal for your wireless mic receive, thereby reducing the potential interference, the potential noise floor, again, increasing your signal-to-noise ratio. Great question. Very difficult to implement in practice other than those two scenarios. So I would avoid it. Even PWS, I just spoke to Jim Van Winkle, the general manager, and he asked me, hey, should we just make the left hand a special order? And I recommended you do, because people are doing point-to-points now. And if you screw that up, instead of getting a great lock of 30 dB of passive gain, you know, that's turning a quarter watt into, 10 watts, basically. Instead, you're attenuating the signal by 30 dB because you got opposite polarized antennas.
Sure.
So, it's a great idea, but put a big L behind one, a pink with purple L, and then the other one, a green and red, R, and never the twain shall meet.
Yep.
or TXRX, whatever it takes.
A question from Sam Balk for zone receive with, say, an MAT 288 or a zone 4. What are your thoughts on switching zones manually as performers move throughout a space versus keeping them active all the time?
Okay, so that's a great question too. And I've done all of these and I've made all these mistakes. And that's why I do these webinars, to save everybody else the headaches that I went through when I've done this. You think that you're going to be able to switch those RFs from zone to zone. And it's a great concept until they say, oh, sorry, we forgot to tell you, the host is going to be in zone 1. This artist is going to move to zone 2. And I want this to work in zone 3. So it's best to have a good antenna system that works in all of your zones, because then you can go use the restroom when you have to. You know, there's a lot of reasons to minimize your headache on site. And that zone switching, yeah, it sounds good in theory. I've done it. And day one, I realized it was a mistake. So you just have to hook up an active, something unity gain. That's all you want is unity gain. I'll even take a couple of dB loss if I have to. And I have.
Is it possible to have RF saturation in an in-ear pack if an artist is too close to a transmit antenna?
Yeah, sure. This is great. This is a good question. First off, again, if you remember earlier, the slide from Sennheiser, the front end of a wireless for audio, you know, audio products, our business wireless system, very dynamic. You can go from a microvolt to, you know, to 1,000 microvolts. In the case of the Shure PSM 1000, there's a linear, like an AGC. And when the RF signal is seen as strong by the receiver pack, it actually attenuates that signal, thereby pushing down the RF noise floor as well and maintaining a perfect signal to noise ratio. If it doesn't see much of its own signal from its own transmitter, that you have, I think it's 30 dB of gain in this RF receiver pack that cranks up the RF 30 dB. And that's when you're asking for problems from lighting walls, other electric fields. And that's why you want to keep your transmit antenna. I'd rather oversaturate an in-ear than undersaturate it.
And what happens when, if you were to oversaturate? Is that going to get a drop? Is it going to?
No, it's not going to get a drop. Okay. I can't imagine. The only thing that could possibly happen is you would smoke a component and the artist would go down way before the pack, I would think.
Sure.
So you would know. And then if they go down, then, you know, get a different pack next time because that one's smoked. But I don't, it would be very difficult to do that.
A couple more questions here. With a diversity receiver, is it okay to use a paddle antenna on A and an Omni on B, or will I run into complications?
No, you won't. You can use whatever you want because the diversity receiver has two complete independent receiver strips. So they are independent of each other. They don't care what the other antenna is doing. The switching is done by monitoring the RF level at the antenna. And the audio is switched based on which one has a higher level, but they are completely two independent systems. In most cases, there are some systems that use a different technique, but they're close enough for government work for us to talk about.
Great. This is from Roland. How do I combine 16 IEM into 12 antenna?
That's going to be rough. You can get, well, you could use RAD. Has a TX8, which will get you to a 1/4 watt. As soon as you marry those two outputs, you're down to 125 milliwatts. And now, what do you say, 12 antennas? Then you're going to be down 369 dB from there. So now you're taking 1/4 watt, which is like what, 21? You're going to be putting out about, not bad. I mean, 20 milliwatts. So you would end up with somewhere between 10 and 20 milliwatts per antenna. And then if you put them on a helical, you're going to kick that back up to a reasonable amount. So it could be done. You know, it's going to cost you. It's going to be expensive. It's going to be like 15 grand for the antenna system. But it's absolutely possible to do. Easy, not easy, expensive, I guess would be the best.
We've got a question from Chris. Is there a handheld RF scanner that you recommend? What about a cost-effective or kit scanner? Yeah,
so that's a great question. You know, I've tried to buy every single scanner that I could afford, but the first one broke me because it was a $25,000 Roden Schwartz. I wish I'd have brought it now, and we're going to get into this in the next discussion. I like the TTI myself. It's reasonably priced, and it does a lot. But that's really a topic for the next thing.
Great. We'll continue that in our next
I got about another 5-10 minutes before I actually have to bolt.
Great. Great question from Brad here. What is the most frequent mistake with antennas you see in the field?
That's a good question. I suppose placement, where you place it. You know, you could get almost any antenna and make it work, but if you put it in the back of a rack and it's surrounded by metal equipment and, you know, metal, it's a cantenna. You've created a cantenna. So I think placement is the, you know, think line of sight. Picture that RF traveling through space. Picture it being a light.
Sure. Question from Mark. Do the same principles apply to 2.4 systems in reference to polarization, reciprocity, and resonance?
RF is RF. That works whether it's a satellite or a CB radio at 20, you know, kilohertz.
Sure. I think at that point, the technologies are using, especially with digital 2.4 transmissions, it's encoding the signal differently and using different types of transmission at that
Absolutely.
point.
But with respect to antennas,
sure.
With respect to antennas, an antenna is an antenna and RF is RF. But yeah, we actually are going to get into FM digital spread spectrum next month.
Great. A question from Kevin. Can we list below where to get the various filters and amps that you've been talking about? So you mentioned that quickly before, some of the different inline filters.
Sure. So there's a bunch of them out there. I mean, Professional Wireless Systems makes little inline. Here, I'll grab one. I have a couple of them here. This one is a PWS filter. It's a little small box. It's about 120 meg wide. Electrosonics makes them. Sennheiser makes them. Shure makes them. RF Venue makes them. This one is a little tighter. It's a cavity filter. You can open up these, and this is a 6 meg wide filter. You can actually tune it, and I like that about it too. That's my favorite part.
That's great.
Just like radioactive design stuff. So there's almost everybody makes a filter. You could start with PWS or RF Venue. Those are two. And then, like I said, most of the manufacturers make filters of varying bandpass.
Great. And another question on that is, what are your thoughts on using bandpass filters with digital RF?
Doesn't matter. Absolutely. RF is RF. Yeah. I do it all the time. If, you know, people think, oh, it's digital, I'll never have a problem. Guess what? You might not know you're going to have a problem until it happens. That's the difference. With analog, at least you could hear the noise. Digital sounds great, and then you get in show, and it just drops out.
Sure.
So filtering, absolutely on digital.
This goes back to our question about using multiple transmit antennas for in-ear systems.
Okay.
So John asks, with multiple transmit antennas, could you cause a bad null potentially if you're using the same transmit frequency on multiple antennas?
Okay, it depends. If you're splitting one transmitter, then no, because of the FM capture effect. If you have multiple transmitters on the same frequency, it won't work. It just won't work. You have to take a common local oscillator from the transmitter itself, the base station, let's say PSM 1000, or even like a rad com or whatever, one signal and split it works great. If I were to take two rads or two PSM 1000s, won't work anywhere at all.
Great.
You could split that antenna as many times as you want. You could have a dipole array that, you know, covers a football field and it'll work great, as long as it's split from the common source.
Great. What was the name of the filter that you just showed that was made in the U.S.?
Oh, this is
the brand of that one.
This is called a microwave filter, and they make them in UHF. Incidentally, it's also the one I had in my PowerPoint under filters. They were UHF cavity tuned. These are cavity filters. Microwave filter is out of Syracuse, New York. I think out of Syracuse, New York. They're about $100, worth every penny. Really easy to tune.
Going back to some questions about antennas in the future as well. So do you envision a future using magnetic loop antennas on mics or Iems to reduce electrostatic interference from LED walls and other sources?
It's a great question. I don't envision it in the future. I envision it in the past, and we put it on the rad belt packs originally for that very reason. Yeah. If you look at our videos from you know, our NAB shows, that was a magnetic loop antenna because of exactly those reasons. We ended up going with a different antenna because of manufacturing costs and the precision of it, but it's in the past. It's not in the future. So I guess the answer is yes.
And the next question is, what do you think the biggest advancements or changes with antennas for the future?
I would really like to see more patch fractals instead of whips. That's the biggest thing.
Great.
You know, nobody likes whips. You know, I did a show with, I think it was Beyonce, and she had the in-ear pack on her back, and then these two antennas sticking up. She's like, I can't wear that. You know, it's going to look like a robot or something. So, you know, if there were patch antennas, it wouldn't have been a problem. It wasn't the receiver. It was like My Favorite Martian. You know, it was not tolerable for the costumer and for the performer.
Sure.
So I'd like to see Pat. That would be my, and it's so easy to do. You know, there's an antenna connector. You don't even solder anything.
That's great. Well, I think that brings us to the end of the questions that we have at the moment. If you do have any additional questions, feel free to email us at sales@tcfurlong.com. James, thank you so much for your time today. This was very informative, and we're looking forward to learning more about you know, your tactics for, you know, everything else beyond the antennas of zone planning or band planning, for instance, which will be at our June 22nd webinar.
Yeah, I'd really love to hear actually if people could send in requests on what that content should be, because obviously we'd speak for hours about this. So I'd like to focus it on what your attendees want to hear.
That's great. And so in our registration link, Aaron, if you could drop that into the chat as well, we do have a section for questions and comments. And so feel free to ask as many questions as you'd like there as you're signing up for the June 22nd webinar, and we can help tailor our information for that as well.
All right, thanks. Thanks.
Yeah, so I want to say thank you again, James. Thank you to Aaron on our team for helping us out here in the background with the video switching and all the Zoom. Thank you for everyone attending. We're happy to have, you know, so many people here and asking great questions, you know, participating in this. Again, I have a slide here for the strategies for large-scale wireless system deployment on June 22nd. We hope that everyone here can join us for that. Again, we will send an email to everyone that registered for this webinar with a link to the new for the June 22nd webinar, as well as a video on YouTube once we get this posted.
If anybody wants the PowerPoint or my email, feel free to share that if you receive such an email.
Yep, great. I'll just ask if anyone wants the PowerPoint, please email us again here at sales@tcfurlong, and we'll be happy to help you out with that. So with that said, James, thanks again for your time today.
Thank you very much, guys. We'll see you.
All right, take care.